live. Here we go. You'll also see I posted a new set of notes called Limits and Continuity. It's inside of the AP Review folder. We're going to go over some of those problems in just a minute. So if you want to start to get that ready as well, you can do that. But I'm just going to show you a website here that I've linked in that folder. I find it really helpful the way that they have kind of structured this as a study guide. I was going to try and put together a study guide, but I kind of really like how this is set up for you all already. And so I've shared this with you. It has kind of the explanation of the exam at the very beginning here, the different units that are being covered and what is not being covered, and what will be on the test and all that sort of stuff. Be careful of the time here, 2 p.m. Eastern. We are Pacific time, so beware of that. We're going to be taking the exam at 11 p.m. 11 a.m. here on the West Coast. And this is information for BC. You don't have to worry about that. And kind of just some like things that you can read through on your own, how to create your study plan, study environment, all that fun stuff. This is where I think that it is very useful. We have here Unit 1, Limits and Continuity, so that's what we're going to start reviewing today. It looks like he has some live streams where he does review, so that's cool. I haven't checked that out, but you can click on there or sign up if you'd like. It has the big takeaways, which is always really nice to make sure you understand those big takeaways of each unit. What is it that I need to understand? What is the basic idea here? And then it has specifically what is the different things that you should be able to do and that you should be familiar with. So you have the different methods of finding limits. Remember, we spent a lot of time going over all the different methods, not only just from table, graph, and algebraically, but we did, when we were looking algebraically, we looked at the limit properties and the rationalization and common denominator and all those things that we did. Oops. Infinite limits, squeeze theorem, all of those are going to be fair game on the AP exam. So things that you should be familiar with. Intermediate value theorem. We're going to go through some examples kind of touching on all of these different parts. But then what's also really nice is that they've linked different resources for you here that you can kind of click through and watch videos and things explaining. And then it also has all of the theorems and formulas all in one place. And this is kind of like the most important, not the most important part, there's a lot of important parts, but this is nice to have because remember on the AP exam, you can have this sheet with all of the different formulas and theorems on you. Normally on the regular AP exam, any other year, you'd have to memorize all of this. And look at all of that you have, that's just one unit. And you have normally 8 units that you have to memorize. So use this to your advantage, right? Compile a list of all these different formulas and theorems. They have it for every single unit. So you have Unit 2 and all the formulas and theorems, Unit 3, Unit 4, all the way through. So I think this is a really awesome, really good resource for you to use to help it guide your studying and give you an idea of any gaps that you may have or you may feel you need to fill in by reviewing a little bit more. This is going to be really great. I'm going to try and keep sharing different resources with you each day. So this is the resource for today. It's fiveable.com or .me, whatever it looks like. I've linked it on Schoology, so you can just click the link and then you have this. And then also at the very bottom, sorry, I'm gonna scroll. Oops, too far. These are some pretty cool links too. So you have this first one is Quizlet decks. So even though you technically don't need to have things memorized, I still really recommend that you do memorize or learn or, internalize a lot of these different definitions, because remember, you only have 45 minutes. So you don't want to spend forever looking things up when you can just know it. So I really recommend you try going on here. You can see it's separated, it's by unit. So if we're working on limits and there's some parts that you want to practice, then you can do that. Let me open a new tab here. Go in, practice the Quizlet, practice to memorize the theorems and the different derivatives and integrals and things. So this would be a really, really good resource, I think. And then, now it's all taking forever to load. Free response questions from past exams, since this exam is going to be solely just free response questions, then I recommend you look on there. But remember also AP Classroom has free response questions for you on there. So definitely look at those AP Classroom questions first and try those out. Not just the ones that I've assigned, but there's some that you can go in and just look for yourself and practice some for yourself. So I recommend that you do that in your own time. And then lastly here, a calculator is not going to be required for the AP exam. However, we all know how much nicer having a calculator can make things. It can make your life a lot easier. And if you have the right functions on your calculator, then it can make things a whole lot easier. So if you have time, I recommend taking a look at this link as well, calculator functions that'll save your life, because it will hopefully be helpful. If you have your calculator and you want to use it during the test, then I recommend checking that out. So this is a resource you want to keep handy, you want to start looking at now, and I'll be showing more as we go through, but that's the one for today. And now we're going to go into our notes. So I'm going to open this up on Notability. I shared it in that same folder where it says AP Review. Just a couple of limits and continuity problems that we'll kind of discuss together. It's not the entire scope of everything. I just tried to pick a few problems that I felt kind of gave you the gist of what you should know when it comes to limits and continuity. So, of course, you can always go in and, practice more. Going into AP Classroom. Okay, so this is what the notes look like. Just has limits and continuity at the top. And what I did was I linked the College Board review session. So they have been posting videos on YouTube, reviewing and going over different units. And so this is their review session on limits and continuity. They have very similar kind of problems as well. to what I'm going over. So if maybe you need a little extra explanation or you need a different kind of explanation, then that'll be really awesome. And I really recommend you just go on and watch it. It's really helpful information that they're giving on there. So that link is there for you. And from there, you can always check out the rest of the videos on there if you want to get a head start on the different topics. You can do that. They have all of the units up there at this point, I believe. So that's there for you. But let's talk limits. So remember, we have different ways that we can find limits. This first example is limits graphically. So the limit as x approaches -5. In order to find a limit, we have to check both the left and the right side. And remember, they have to come to the same y value in order for the limit to exist. If they have different y values, then the limit does not exist. So in this case, limit as x approaches -5 of f of x, we have to check both sides of -5. This is -5 right here. And I see that on the left side, it's approaching -infinity, and on the right side, it's approaching +infinity. Since they're going in different directions, then this limit does not exist. So we already have one that does not exist. All right. Next, it's asking for the limit as x approaches -5 from the right. Remember that little plus symbol means from the right. So what I will do is I will follow the function. On the right side, this is -5. On the right side, I'm going to follow it going in towards -5, and I see that the function is going up to +infinity. So my limit will be +infinity. So -5 total limit does not exist, but -5 from the right is +infinity. Next, we have the limit as x approaches -1. So -1 is right here. We have that point there. We see that both sides are meeting at that same point, and that is at a y value of 1, 2, 3, 4, 5, 6. So our limit will be 6. Oops. All right. Next, we have the limit as x approaches 3. 1, 2, 3. Now, we have a hole, but remember that limits can be holes as long as the left and the right side are still coming to the same y value, which they are in this case. They are both reaching +3. So the limit is +3. Next, I can't talk. Next, it is asking for the limit as x approaches 3 from the left side. So again, we're approaching the same x coordinate, but now we don't care what's happening to the right. On the right side, it could meet, it could not meet, doesn't matter. But we follow the function towards +3 from the left side, and we see that it's still approaching 3. So our limit is 3. And lastly, the limit as x approaches infinity. So here's our x-axis. X is approaching infinity, so I follow the function. As my x's are getting bigger, my y value is not going to go any lower than this value here, which we have a horizontal asymptote at -2. So that means our limit as x approaches infinity is -2. So remember, anytime we're finding limits approaching infinity or -infinity, that's finding horizontal asymptotes. So all we had to do was look to see there's a horizontal asymptote. So then that asymptote is at y equal to -2. So that's going to be our limit in this case. Okay. Please let me know if you have any questions as I'm going through these problems. I'm going to go through them rather quickly just because it is review, but hopefully we got kind of sparks starting to flare up because you remember going over this before. So let's go on to the next problem. So now we're getting into some algebraic solving. So the limit as x approaches 3 of x squared minus 9 over x minus 3. Remember that we always want to start with direct substitution, but when I plug in 3, I get a 0 in the denominator, which makes it undefined. So we need to try and simplify this before we can do direct substitution again. And I'm going to do that by factoring. And that's the difference of two squares up top. So I can break that down and cancel out x minus 3. So that now this becomes the limit as x goes to 3 of x plus 3. Now I can do direct substitution. 3 plus 3 equals 6.
Miss Monty, is
That
this
was our factoring method to solve the limit. Let's take a look at number 3.
Miss
The
Monty?
limit as x approaches 4 of root x plus 5 minus 3 divided by x plus 4 times x plus 1. So again, if I plug in 4 here, direct substitution, I'm not going to get a 0 in the denominator, so that's not going to be an issue. We can go ahead and plug that in. The limit as x goes to 4. Sorry, I said I was going to plug it in and I started writing limit. Once you plug it in, remember you don't need to write the limit notation. Yes, this should be posted on Schoology. Just look at the folder that says AP Review and you'll see this in there. So we're doing direct substitution. Sorry, I don't know why my screen's not kind of acting weird. Okay, so this will be 4 plus 4 times 4 plus 1. And square root of 9 is 3 minus 3. 3 minus 3 is 0. So 0 divided by anything is going to equal 0. So there's that example. Wasn't really too exciting because we didn't actually rationalize. But let's see if we can do a rationalizing example. Let me see. I'll try and get one. We'll come back and I'll see if I can get a rationalizing example for you. So let's take a look at number 4 here. We want to find the horizontal asymptote of the function f of x equal to root 4x squared plus 7 divided by 3x minus 5. So in order to find the horizontal asymptote, remember I said earlier when we were looking at the graph, what we want to check is what is the limit doing as x approaches infinity, and then also what is the limit doing as x approaches negative infinity. So in both directions is what we want to check. And we have root 4x squared plus 7 divided by 3x minus 5. All right. What we want to be able to do is apply our our rules for horizontal asymptote. So we want to check to see, is it top heavy, bottom heavy, or same degree? But in this case, we have that root at the top, so we have to actually square root it. And before we kind of get into that part, we're checking the limit as x approaches infinity. So we're thinking about plugging in really, really, really huge numbers, right? If we have a really huge number, you're multiplying it by 3, so you're making it even bigger, and then you're subtracting 5. Is that going to make that much of a difference if you subtract 5 from a really, really, really huge number, an infinitely large number? It's not going to make that much of a difference, right? So if we have 3x minus 5 in the denominator, it might as well be, for the sake of us seeing what's happening as x is approaching infinity, it might as well just be 3x. That minus 5 won't really make too much of a difference. In the numerator, we have 4x squared plus 7. Again, x is now being squared. So if x is already an infinitely large number, and that infinitely large number is getting squared to make it even bigger, is adding 7 really going to make that much of a difference? Not really, right? So we can think about this as just square root of 4x squared divided by 3x. So now, and this is still the limit as x goes to infinity. The square root of 4x squared is going to be 2x, just as long as x is positive, so I can write absolute value of x. Oh, I don't know what's wrong with my screen. It's not writing. Okay. Like that. So now we've gotten to the point where we see it's actually the same degree in the numerator and the denominator. And so if we plug in a really large number and it's a positive number, then we know it's just going to be 2/3. The coefficient of those two terms there, 2x and 3x, its coefficient is 2/3. So as the limit as x is approaching infinity of our function plus, I don't even remember what it was, 4x squared plus 7? Yeah, divided by 3x minus 5 will equal 2/3. Now we also want to check on the negative infinite side to see what is happening there. So same idea. This ends up just becoming absolute value of 2x over 3x. But now x is a really, really negative number. So technically a really, really small negative number. And when we plug that in, the absolute value will keep it positive in the numerator, but it's going to be negative in the denominator. So this will actually turn into negative 2/3 in this case, as we are approaching or going towards negative infinity. So we have two horizontal asymptotes in this case, one going towards 2/3 and then the other going towards negative 2/3. All right, that can box that in as well. So the idea here, when asking for or when checking for horizontal asymptotes, you want to check the limit as x approaches infinity and the limit as x approaches negative infinity. So both. Okay. Number 5, I didn't really leave too much room here. That's might be a problem. Let's see. We want to find the value of k that makes the function f of x equal to x squared plus 2 when x is less than or equal to -1, and kx plus 4 when x is greater than -1, continuous for all real numbers. So keyword here, continuous. We've got to know, when is a function continuous? What is the definition of that going to be? So let's talk this through. There are 3 things that need to be true in order for a function to be continuous. I wonder if we remember what those are. So the first one is the limit. Let's say if we're checking continuity at a, the limit as x approaches a has to exist. So we're checking if it's continuous at x equal to a. Let's just say, for example, the limit has to exist. So in order for a limit to exist, the limit from the left and the limit from the right have to be equal. They have to be the same. So that's kind of like a sub rule here. Okay, so the limit from the left and the right have to be equal. And so then that way we know that the limit exists. Number 2, we have to know that f of a exists. So by the limit being true, that means that from the left and from the right, it's approaching the same kind of direction there, right? That's what the limit existing does. F of a existing just means there's a point at that value. So if this is a here, right, if f of a exists, that means there's a point. But then the last thing that needs to be true is that the limit as x approaches a has to equal f of a. So that means that point has to fall in line with that limit. So that way now, since that hole is filled in, it's one continuous function there. Okay, so that is the definition of continuity, how to prove if something is continuous. So now in this problem, it says that we want to pick a k value that's going to make it so that this is continuous. So we're going to work through kind of these steps to show what that continuity would look like. I wish I had given us more room. I don't know why I didn't do that. So we'll try and squeeze as much as we can in here. So here we have x squared plus 2. We're checking continuity, obviously, when x is equal to -1, and this is x less than or equal to -1, so that's the left side there. And so let's kind of write this out here. And then the right side, x greater than -1, is going to be kx plus kx plus 4. Okay, so our rules to finding limits is just use direct substitution. So this limit on the left, all I have to do is plug in, I don't know why it's not writing well today. Let's see, -1 squared plus 2. There we go. And on the right side, same thing. just direct substitution. So remember, when you have that little symbol, the minus and plus, that means left or right. If you're solving algebraically, you can kind of just disregard that and do just direct substitution. So this is going to be k times -1 plus 4. Since since x is what's approaching -1. So I'm plugging in to those x values. So this gives me an equation that when I solve the equation for k is going to give me the k value that makes this all true for us. So this is going to be 1 plus 2 is 3 equal to -k plus 4. Subtract the 4, that's going to give me -k is equal to -1, so k is equal to +1. So that's the k value that's going to make this function continuous at x equal to -1. So technically that would mean the function has to be x squared plus 2 and x plus 4. And obviously the problem isn't asking you to rewrite the equation, it just wants you to find the k value, but there you go, that's the k value. Okay, so you're using what you know about what needs to be true about continuity and setting that up so that you can then kind of solve from there. Sometimes that's all you got to do is look for the theorem or the definition and start with that theorem and definition and work your way down from there. Plug in what you know, and then it kind of sets itself up for you. You just kind of have to simplify it. Oftentimes that's going to be the case. So that was number 5. Number 6 says the function f is continuous on the closed interval from -2 to 2. Several values of the function f are given in the table below. So we have a continuous function. That means there's not going to be any breaks or any holes. And there's the table. The equation f of x equal to 1 must have at least 2 solutions in this interval from -2 to 2 if c is equal to what value? So this, let's kind of break this down here. Because we have a continuous function and it's continuous on the closed interval, and we're talking about finding things within an interval, we're going to think intermediate value theorem. Okay, that's the one that we're going to think here. So the intermediate value theorem pretty much says if you have a point up here and let's say a point down here, then since the function is continuous, there's going to be some point that exists within those 2 points that is a 0, right? Or that, you know, whatever this, let's say this is 4 and let's say this is -2, then we know that y equal to 3 has to exist because 3 falls between -2 and 4. So that's what our intermediate value theorem does, is it proves that there's something that is within an interval. So what we're trying to prove here within the interval from -2 to 2 is that the equation here, f of x equal to 1, or in other words, like y equal to 1, has at least 2 solutions in the interval. So it crosses through the x-axis at least twice, depending on this c value. So I can do like a quick little sketch here. -2 and 3 is right here. and 2, 2 is right there, right? And this is a continuous function, so I know that somehow these 2 points are going to connect, right? But it could be something like what I just drew, it could be something like that, it could be something like that. And actually what I just drew right here is what we want to show, because we want it to have at least 2 solutions in the interval. And actually I just realized this is supposed to be multiple choice, because otherwise there's an infinite number of values that could work here. Let me pick out, I think I have the problem right here, what those options are. Here we go. So we have option A is 1/2, B is 1, C is 3, and D is 4. Okay. So those are our options here for what C can be. And so it's saying that the equation f of x equal to 1 must have at least 2 solutions. So actually, sorry, earlier I misspoke. We're trying to look for when it's crossing through this line, because this is when f of x is equal to 1. When is that going to cross through? Twice, right? So if I were to draw something like this, that wouldn't work. So that means our C value here, and I'm looking specifically when x is 0, so I'm looking specifically here, right? This C value cannot be 3 or 4 because that's too high of a value, and that means that the function isn't guaranteed to ever go down and through that green line, right? So I can eliminate those options there. And then we have B, which is 1. And if I were to try and draw this, oops, to go through 1, does that guarantee that it's going to ever cross through again? No, not necessarily, right? What would need to happen is we would need for when x is equal to 0 to go at least to 1/2, because when we do, we see that now this crosses through twice. Crosses through this f of x equal to 1 line at least twice. Okay, so our answer is A, 1/2. All right, so it's using that intermediate value theorem. Because we know it's continuous, we know that there's going to be kind of some pattern that we're going to be able to follow and check to see if it's going to go through the solution or not. All right. Questions, let me know. We've got just one more problem here. So we are doing pretty good time here. Me just talking a lot. But hopefully things are kind of coming back to you and you're kind of remembering how to do all of this. Or if maybe you didn't fully understand it the first time around, things are hopefully starting to make a little bit more sense, or pieces are starting to kind of come together a little closer. That's our goal here, at least. So now we have this last problem. The limit is x goes to 0 of x cubed times sine of 1 over x. If I do direct substitution, there's already a big, huge problem that I see is that right in here, I'm going to get undefined. So how am I going to find the sine of some value that is undefined? That's not possible for us. So we are going to use what we know about sine in order to kind of work our way through this problem. So what do we know about the sine graph, the y values of the sine graph? It's going to fall in between two numbers. It's going to fall in between -1 and +1, right? So we're starting with that information there. Because we know that to be true about sine. Okay. So it's going to have to fall in between -1 and 1, and obviously it's going to be equal to 1 and -1 at certain points as it goes through and oscillates. And what we want to do next is in the middle, we already have sine of 1 over x. We need to incorporate that x cubed. So I can go ahead and multiply all the way through by x cubed. So this now becomes -x cubed, sine 1 over x, and x cubed, like that. So that we have created that same function, and we want to take the limit as x goes to 0 of that function. So I can take the limit as x goes to 0 of this whole thing, just like that. I do direct substitution on the left side, so the limit as x goes to 0 of -x cubed. That's going to equal 0. This middle one is the one that we are still trying to solve because we can't do it using direct substitution, not in the way at least that we're used to. And on the right side, if I do direct substitution for that limit problem, I get 0. So now the limit as x goes to 0 of x cubed times sine of 1 over x has to be in between 0 and 0. So it's squeezed between 0 and 0. I don't know if anyone remembers that theorem, squeeze theorem. If it's squeezed between 0 and 0, that means that it has to equal 0. Because there's no other way if this limit is in between 0 and 0, there's no other place for it to go other than to 0. So that makes this limit equal to 0. So we had to use the squeeze theorem in order to prove that. So there you go. So that was like our quick kind of review of limits and continuity. Obviously, there's a lot more that goes into it and that we talked about. So that's up to you to go back and review and look at all those different properties and theorems that came up. We will be doing more problems eventually, practicing that and kind of combining everything all together. But I want to start out by each class kind of refreshing you on the different topics, the different units that we've gone over. So that was our quick overview of limits and continuity. Again, I recommend that you go onto AP Classroom and practice problems within that unit, which is Unit 1. Another thing that I want to kind of show you all And this will kind of help you with reviewing because we have about 10 more minutes, so we have time for me to show you this. That's not what I want to show you. So we're not going to actually watch the video. Uh-oh, I got disconnected. Hang on a sec. But instead, what I want to do is I want to show you the whole catalog of videos that they have available. So this is the Unit 1 limits review, and then you'll see here on the side, they have all the units, so Unit 2, Unit 3, 4, 5, 6, 7, and then they have some mixed review, and then what you'll see here is the different kinds of free response questions. So there's two things that you should be studying and preparing for. One, obviously, is the content, right? You want to know what's going to be on the exam, all the theorems. You want to know how to solve the problems pertaining to that content. So that's what we're going over right now, right? We're talking about limits, we're talking about continuity and, the definitions and all that stuff. But then there's specific kinds of questions that the AP, that College Board normally uses on the AP exams. And so you'll see here, they go over those kinds of questions. So the first one is a tabular free response. So that means it's a free response question that involves a table. They give you a table and you have to be able to analyze that table and use the information from that table and apply it to whatever theorem or definition that they're having you recall. So that's going to give you tips on how to use that table to solve the problem. Then you have the graphical STEM free response questions. So when they give you a graph, how do you use that graph? Where do you go from there? How do you break down what you see in that graph into information that you can then use to be able to solve your problem? And then verbal scenarios, so word problems pretty much. How do you break those down and how do you understand those and get the information that you need in order to solve your problem? So those are the three types of questions that you will see most likely come up in your AP exam. So you want to be familiar with that format, and you want to be familiar with the different tips and tricks on making it easier for you to get through those questions. So that is on there for you as well. I really suggest that you go through it. We're going to do problems together, and I'm going to point out things that work for me, but it's always helpful to hear from other people what works for them, and you're a sponge. You're soaking it all in, and that's what you're going to use for the AP exam. So there's great information. I've watched a lot of these videos, so I can say that it is really useful. So please make sure you go on there as you're preparing and reviewing for the AP exam. I may show little snippets here and there as we're kind of reviewing, or I may take problems from those videos and we can do them together. Or if you have any questions on any of those problems, you want me to help you with it, that's also something you can do. But I'm trying to put as many resources at your fingertips as I can, so that you can take the liberty to structure your studying the way that is going to work for you. So that is going to be it for today. Please let me know if you have any questions. Remember, you have that AP classroom assignment due Friday at the end of the day. I will be posting some practice problems to go along with the limits, to go along with the notes that we went over today. I don't have those ready just yet, but I'll have them up probably by tomorrow in case you want to practice. But then also, there's AP Classroom. You can go on there yourself and practice on your own time. All right, that's enough of my talking for today. I hope you all have a great rest of your day, and I will see you on Friday for our last class of the week. You're welcome. Goodbye. Bye. See you guys. Goodbye.